But this is the important that in times of crisis, without educations, we do not have better overall health, no civic involvement, no crime will be decreased. So this is a very important things that we should continue the e-learning. However, but we have to know how it would be materialized and how it should be very is distributed to all over the students who would like to have these things. And I must say, medical physics, how the technologies is upgrading day by day is very important. We only through e-learning, we can reach the expert, we can reach the technology, and we can reach the everything. But we should be very patient and hearing for these things. Thank you all.
Thank you very much, ma'am, for such an active interaction. I apologize for being a little in panic because of some local examination, we do not have internet connection in the city, so I have to go to some third-party meeting. Anyways, we are in the middle of the school, so I think I should hand over all of this program to Anupama ma'am, and she will. I think now we have Professor Jayasingham for the lecture.
Yeah.
Yeah. So I won't take much time. I will directly hand over to him. Then we should go ahead with that.
Okay. Our next speaker is Dr. Jayasingham Jayasugithan, and he is currently a senior lecturer at the Department of Nuclear Science of the University of Colombo and associate of International Center for Theoretical Physics, ICTP, since 2019. He received his PhD in physics in proton beam radiotherapy in 2014 from the University of Cape Town. He has more than 10 years professional experience in clinical radiotherapy and radiation protection as a medical physicist, worked under Sri Lankan Scientific Services. As an academic medical physicist, he has been accredited as a teacher in higher education by Staff and Educational Development Association, UK. After completing of MSc in Medical Physics at the University of Peradeniya, Dr. Jayasugithan joined the Teaching Hospital Jaffna in 2005, where he worked as a clinical medical physicist and RPO at the Cancer Treatment Center, Telipalai. Dr. Jayasingham has participated IAEA expert mission to assess the status of cobalt-60 treatment machine and assess the overall clinical radiotherapy treatment. IAEA Technical Cooperation Project, Tulai, Papua New Guinea, May 2018. In addition to being a director of the Sri Lanka Atomic Energy Board, presently he is coordinating postgraduate and training program for medical physicists and radiographers. Currently, he is actively studying the optimizing patient dose during the diagnostic radiological procedure, which is timely, important, and urgent in Sri Lanka. He is also focusing research to other areas such as radiotherapy, nuclear medicine, and radiation dosimetry. He is presently supervising several PhD and MSc research projects. He is a member of Sri Lanka Medical Physics Society and member of Scientific Committee of AFOMP, IAEA National Project Coordinator, Editor-in-Chief, the newsletter of South Asia Center for Medical Peace and Cancer Research, Program Coordinator of the Postgraduate Degree in Medical Physics. He is serving as a member of various committees at the faculty level. Thanks, Dr. Jaya. Please, I'm giving you floor to continue your lecture. Please share your lecture.
Yeah. Thank you very much, Professor Anupama, for the brief introduction. So now you can see the PPT, no? Yeah. Okay.
Yes, it's okay. Please continue.
Yeah. Okay, thank you. First of all, thank you very much for giving me this opportunity to talk about the establishment of DRL for commonly used radiological procedures. So first, definitions. So definition for DRL, based on IAEA definition, so DRL is a level used in medical imaging to indicate whether the dose to the patient or the amount of radiopharmaceutical administered in a specific radiological procedure for medical imaging is usually high or low. The second, from ICRP, based on ICRP, the definition is DRL is a form of investigation level used as a tool to aid in optimization of protection in the medical exposure of patient for diagnostic and interventional procedure. So these are the definition from IAEA and ICRP. So based on this definition, DRL is not a patient dose. The DRL is some quantity or related to the patient or correlate to the patient, so that you can, if you have a DRL quantity, then you can see whether your facility is high or low. So again, it is not a patient dose. So, but allow us to estimate the risk level to individual. So actually the patient dose depending on several factors. The patient dose depending on the people, adult or pediatric or female or male, depending on the ethnicity. So depending on several factors, and also depending on the patient size and shape or patient inhomogeneity. Also depending on protocol, examination, type of examination and type of protocol, depending on the modality, CTO, the DR system or CR system or X-ray or mammography or nuclear medicine. Also depending on the type of detector, manufacturer configuration, type of detector, type of scanners, depending on the diagnostic questions. And depend, I think today Professor Sataria is going to talk about the quality control in diagnostic radiology. Yeah, also depending on the condition, depending on the radiologist, depending on the radiographers, so many factors. Also depending on the exposure control, automatic exposure control for MA4 and KB, and depending on the scanner factors, parameters, KB, selection of KB, MA, filtration, pitch value, FOV, and finally depending on number of radiographs per examination. So if you have a repeat scan, the patient get more doses. So now you can think about, you can see here, so a lot of factors not depend, that patient dose depending on not only the single factor, but overall dose depending on all those factors. So I'm not going to discuss in detail because 30 minutes is not enough to tell everything. But you can go this website, the IAEA website. Then you can get all the basic knowledge or information you can get from this website. So now that I'm going to discuss next the most important points. The first DRL were established into 1980s. So then subsequently developed for other modalities, for radiograph, conventional radiograph, then subsequently developed for other modality from to 1990s. So the DRL should be established to routine condition and procedures, should be established for specific procedure and protocol. So for example, head CT or abdomen CT or chest CT. These are the common procedures we have. And the new trend is establish the DRL for indication wise. So you can go for indication. There are in CT, there are several indications. So you can go for whether you can go for indication wise or you can go for the diagnostics, common diagnostic site. If DRL is not available, the initial establishment of national or typical, I am going to discuss this terminology, the national, typical, local later. The values will be the first steps that is the first steps. So then you had to repeat. So you had to repeat periodically to evaluate changes. Then first, if you don't have any DRL, first steps, you have to establish the DRL. So then you have to optimize your protocol. So I think the next lectures, next speaker will talk about the optimization, how to optimize the DRL. Then after that, you have to repeat this establishments in every 3 years. So initially you can go for every 1 year. Then after that you can repeat it in every 5 years or 5 years, depending on the variation. So you can see here, this is from the data from the UK. The first they established in 1985 for radiograph. This is the value for the entrance surface dose. So in 1985, for example, for skull AP and PA, the 5 milligray, the patient received average mean value DRL 5 milligray. So then in 1995, it was 4. Then 2000, it was 3. Then gradually decreasing. So that they have, because they have the good they implement the optimization procedure, then they reduce the dose every 5 years or 10 years. The sampling, that is very important, that they're always confusing this sample and standard size weight patients. So when you establish that, according to the ICRP, they recommend to establish the DRL for standard patient. So for example, standard patient may be that depending on the country to country, the standard patient weight is different. So in Sri Lanka, for example, the standard adult weight is 58 kilograms. Then you can go 48 to 68 range or different range. But this is very critical, because in the hospital we don't have any patient weight data. So then we have to go for we can establish the DRL based on the weight group. For the pediatric patients, so you should go weight group. You have to divide the patient in different weight group, or if not available, then you can go for the age wise. Weight group is very most important for the DRL for pediatric, because the patients are rapidly growing. Then the facilities. So 30 to 50%. For example, if you have 100 X-ray unit in your country, then you can collect the data from the 30 to 50 percentage. That depending on. Then I will talk later. The sample size, data size, the patient per room per examination. If you go for patient per room per examination, for example, you have several X-ray machines. So you want to CT machine. So you want to calculate the DRL per in each CT machine per protocol. For example, for head CT, then at least you need 20 data, the 20 patient data for radiography, 30 for CT fluoroscopy, at least 50 for mammography, 30 or more for interventional radiography, depending on the dose variability. If you want to go for patient per procedure per patient group, so if you want to do it in age group or weight group, then at least 10 patient per procedure per age group. At least this is for radiography, the 20 patient for CT and fluoroscopy. So this, if you want to establish the national wide, this is for local, for hospital wise. If you want to do it for national wise, so you have to, if your country is very large country, then you have to cover the 20 to 30 facilities. That is sufficient first time. Then you can, after that, you can increase the number of centers. You can include more centers when you establish the DRL. For the small countries, if you, for example, if you have less than 50 CT facilities or hospitals, then you have to cover around 30 to 50% of facilities. That is sufficient, because that also depending on the there's a limitation. If you get the convenient sampling, that means readily available data is used. So if you don't have the weight group, then we don't have weight. So then we are collecting the data what they have. So the next, the quantities suitable for setting DRL. So this is this is from IAEA documents. These are the quantities, the DRL quantities quantities: entrance surface AR-KERMA, incident AR-KERMA. These are for X-ray, normal X-ray radiography. So then incidental AR-KERMA at patient, or AR-KERMA area product, or dose area product. So both are same for the diagnostic radiology. So in CT, volume compute, CTDI volume and dose length product. In mammography, mean glandular dose or average glandular dose. So these are the quantities recommended by the IAE and ICRP. So yeah, for radiography, you need AR-KERMA area product or DAP dose area product, fluoroscopy AR-KERMA area product, or AR-KERMA or patient entrance surface dose, reference dose, or that fluoroscopy time. The time in fluoroscopy, the dose, patient dose, depending on the time, depending on the consultant or depending on the surgeon. Time for the examination. So you that also DRL quantity. In CT, CTDI volume and DLP. In mammography, mean glandular dose or average glandular dose, or you can calculate the incidence AR-KERMA rate or entrance surface dose. For dental, again, you can estimate that DAP. For nuclear medicine, activity. So activity administered to the patient. You have to measure the activity. Okay, that this is the important point slides. Then ICRP classify it is in different category, the typical value and local, national, regional DRL, X-ray machine. For example, in your hospital, if you have a one X-ray unit, so then you can estimate the median. So the median value for that X-ray machine, that is called typical value. So if you have several X-ray machine, for example, 10 rooms, X-ray rooms you have in your hospital, 10 to 20. So then you can estimate from median, typical value for each X-ray machine. So then the local DRL, the third quartile of all the median. So you have, for example, you have 10 X-ray unit. Then you have 10 median value, 10 typical value. Then calculate the third quartile from the 10 median. Then that is called local DRL for that institute. The national one, you have to collect the data from all the hospitals. So then I will explain later how to calculate the local and national. And regional, then we can go for the regional wise. So South Asian region or SAARC region or European DRL. So we need to collect the data from each country's national. If we know the national DRL from the each countries, then we can establish the DRL for the regional. So then if you want more details about that the terminology and the method, then you can get from the ICRP document 135. So that ICRP 135 recommend this way, this flow chart for the institutional DRL. First, you have to collect the data based on the weight group. So for average weight, average adult, then calculate the median. So median dose for examination, for particular examination. So then you have to compare with the DRL, country, national DRL. If your DRL is less than the national DRL, then you can, again, you have to review after 3 years. If you more than the DRL, so already established or national. So more than that, then you have to check the performance, the technique. You have to review the technique and exposure settings and equipment performance. You have to check that, and you have to optimize the protocol. Then you have to implement the protocol. Then again, you have to go for the data collection. Okay, now I can discuss how to establish the local and in detail, local and institutional DRL. So you can see here there are 3 hospitals. The hospital, one hospital, Hospital A, it has 3 X-ray rooms, units, X-ray unit 1, 2, 3. In say this is the CT. So then they have 4 protocols. The blue color for say CT, head CT, and other colors for different protocols. Okay. So then take the reading from each protocol, then calculate the median. So that is the typical value for that X-ray unit. You have typical value for X-ray unit 1, typical value for X-ray unit 2, typical value for X-ray unit 3. So all the median you have for different protocol. So then you have to calculate the median of median. So then, or third quartile, if you have many X-ray unit to around 20 more, 10 to 20, then you can estimate the third quartile also. So median of median, normally, usually we estimate for the local DRL. First, you have to choose the quantity. Then if you want to CT, then you have to choose CTDI volume or DLP. If you want to do it for X-ray, then you have to choose the dose area product. Yeah, then national DRL. Now we have local DRL or institutional DRL. So we already estimate that from the each radiography unit. So then you have to calculate the third quartile of all the median. So from median, there are several hospitals: hospital A, hospital B, hospital LM and L. So then get all the data from a particular protocol, say abdomen CT. Then you know the typical value for abdomen CT. Then institutional DRL for abdomen. Median value for abdomen CT. So then from that value, then you can estimate the third quartile of median for each examination or protocol. So that is the national DRL. The first quartile or median is the target. So you know the target value. So you know the current DRL. Then next step, you have to optimize the procedure. The study design. So this is the very nice paper published in Physica Medica. So the flow chart for the national development of national DRL. The first step, you have to call for the application, the participant. So they call the 62 participant hospitals for different 62 type of procedure and 7 surgical procedure. So this is for the fluoroscopy. So then only the 59 centers participant agreed. So for procedure, yeah, I think there's some mistake. The first one, not procedures type, the centers. Then they invited 62 centers, but only 59 centers agreed. So for the number of examination procedure, 47, I think 47 as number of surgical number 7. Then data collection. The third, these are the first two steps. Then third step, the data collection. Then now they got the data. They got 8,840 data from 59 centers for 47 procedures. So then they had to remove the data. They exclude 2,000 data, around 2,000 data, because less data, the missing or incoherent information. So most of the data, there's no enough details. Then they have 7,000 data from 58 centers for 46 procedure. Then again they exclude another 728 data because there are 3 centers. They have less than 10 patient per procedure centers. So then then final step, you have to analyze the data. So then I will discuss these things again. So then you have to plan your study before starting your work. That is very important. Otherwise, difficult. You have to get the permission from the your ministry or any professional body or any hospitals. That's the first steps. So if you got the permission, then you have to start your data collections. Then you have to analyze the data first. You can do the pilot study, and then you can sometimes you have to exclude more data. The final step, the data analysis. So, okay, that the questionnaire also important. You have to design the questionnaire. So before starting the work, because that is very important. If anything missing, then it is difficult to go back and get the data. So then you have to prepare. This is for the CT. So you have to prepare the questionnaire, include all the information, the date of birth, the height, weight, that important, that factors, the exposure factor, KV, MA, MAS. In MA is difficult in CT. If it is automatic exposure control, then you have to collect the range, the minimum and maximum value, or average value, or total and pitch value, DLP, CT. So then also the details about the protocols. So then the presenting data, I'm going to talk now the presenting data. So there are several ways. First, histogram. So you can plot the histogram. So in this case, there are 63 scanners involved in this work, that third quartile. So you can see the third quartile, below the third quartile, there are 46 centers. So above third quartile, there are 17 centers. The red color is the national NDR. So NDR is defined at third quartile. So other histogram, you can plot the histogram like that. Then you can identify the red color, red arrow for the national DRL. Then you know above the national DRL. So another histogram bar chart. So you can plot the bar chart. Here there are 61 centers in Australia. So the 75 fifth quartile values 2.6 and 95 also there. Then now you can see what are the centers below, very lower than the national DRL. Some of comparable with national DRL, and some of them are above the 75th percentile. So then this is very important, that the bar chart is very useful to identify which hospital you are going to optimize. Also, you can compare with other country data. If you don't have a national data or institutional DRL, then you can go compare your data. So this is from our Sri Lanka. Then we established the DRL for abdomen CT. So the present value you can see for CTDI volume 10.5, but it is comparable with Nigeria and Belgium, but lower than the other countries. So this data, presenting data is very important to identify the weakness and strength. That is important step for the optimization. Yeah, also you can see in the, for example, the Turkey. So the CTDI volume for the Turkey is around 13.3, but DLP value is less, very low. Yeah, because the DLP value depending on the scan length. Yeah, this is also from Sri Lanka. This is for DLP value for abdomen. The box plot. The next you can plot the box plot. That also important. So box plot you can see. Again, you can see the hospital, the hospital data, individual data, and you can compare with national data, and you can see which hospitals are very lower than that national data and higher than the national data. Also, you can see the range, the first quartile, second, median, and all the informations are in the box plot. Yeah, another way of presenting data, the table. So you can plot, you can make a table to show that values, exposure values, and also the data for the CTD and DLP, those data, and also you can compare with other country data. The fluoroscopy, that earlier I discussed the CTDI volume. For the fluoroscopy, this is the examination, the DRL. So in DRL, for the fluoroscopy, you have to estimate the DAP value and fluorescent time. So for the mammography mean you have, these are the data we need. The number of images, number of cases, age, and mean thickness, breast thickness, and KVP, MAS, entrance surface dose, Oyakama, and these are the different view, CC and MLO view, the right and left CC view, and we calculate the DRL separately, and MLO view, right and left and average. So then for these are the typical values, the median. So they calculate the median for each institute. So there are 61 institute. Then finally, the overall for the national, that third quartile of all the median. So the final steps, a little bit I'm going to explain that. I think the Professor Sakaria will talk about this more. The performance of perform quality control is very important before for the DRL development. So before collecting the data, then you have to do all the quality control check. First, we have to check whether your machine is working okay or not. So because some data for digital for digital radiography or digital equipment, so we take the value directly from the console. For example, CTDI volume or DLP. So we take the value from the console, from the modern console. Then first you have to ensure the values right or wrong. So then you have to do some quality control check. That, for example, then using this Phantom, you can estimate the CTDI volume. You can measure the CTDI volume and DLP. Then you can compare with the console. Then if it is a plus or minus less than 30% or 40%, it is okay. Otherwise, you have to calibrate the CT and then you have to do the data collection again. So these are the definitions that I think Professor Chakaria will talk about that. So the CTDI content is defined. The integral dose along the 100 centimeter ion chamber divided by the nominal beam width. So usually we estimate the CTDI volume per rotation, per small rotation. So then the dose spread over the 100 centimeter ion chamber. So then weighted the per particular slice, then we calculate the average dose. 1/3 of you have to, for this purpose, you have to collect the data from the center, then of peripheral. The CTDI volume weighted values define 1/3 of center data from the center, ion chamber reading from the center, then plus 2/3 of ion chamber from the reading from the peripheral. So then CTDI volume equal to CTDI weighted value divided by the pitch. So then if you know the pitch, then you can divide by the pitch, then you can directly get the CTDI volume. So if it is helical, if it is axial mode, then pitch value equal to 1. So then CTDI volume directly equal to CTDI weighted value. So then you know this also definition CTDI weighted, then DLP, CTDI volume multiplied by the scan range. So I think the final one. So this is the quality control. Before collecting the data, taking data from the CT, so you have to do the check for all the CT equipment. So you can see here the measured value for first one for Philips. CTDI volume for Philips measured value 62, the console value 65.6. It is the 5 point. The variation is 5.5. So they calculate all this data, the experiment for all the equipment. Yeah, you can get more data from this manual. Okay, I think thank you very much. Again, thank you very much giving this topic. This is the last one.
Yeah. Thank you, Professor. Thank you, Dr. Jayasiganthan. Many thanks for your nice lecture, especially for dosimetry and diagnostic radiology, which is very important nowadays because most of the countries do not have the quality control procedure in diagnostic radiology. So we are going to the next speaker. I'm sharing her CV, short biography for your concern. So our next speaker is Diploma Engineer Catherine Enz, Medical Physics Expert, University Hospital, Frankfurt, Germany. Quick overview of her. From the 2015 till present, she is the active participation in the German standardization body DIN. 2015 to 18, lecturer at the Radiographer School in Münster, Germany. 2011 to 18, medical physicist at the University Hospital Münster, Germany, deputy head of the Physio-Technical Quality Control at the Reference Center for Mammography, Münster. In 2011, Master of Science, MSc in Medical Physics at the TH Mittelhessen University of Applied Sciences in Gießen, Germany. Master thesis as Landauer, Europe in Fontaine-aux-Roses, France. 2010, he is a diploma in engineering, in medical engineering at the University of Applied Sciences in Gießen. Diploma thesis at the Fraunhofer Institute for Laser Technology in Aachen. 2008, the Bachelor of Science First Class Honors in Biomedical Engineering at University of Ulster in Jordanstown, Northern Ireland. So our topic is, he will speech on, I'm just giving the share. Basic dose optimization in diagnostic radiology, verification of dose data, and identification of errors. So I am requesting Diploma Engineer Catherine Enz to start your speech. Thank you.
Thank you very much for your nice introduction. I'm going to share my screen in just a second. Hold on.
Is it okay? Hello, Catherine Enz. We can't see your slide.
Hello, Anupama ma'am. I think we are not able to see the slides.
No, I think it's working now. It's
Yeah,
just I cannot start my video because whenever I start my video, my Zoom conference crashes. So I'm just going to talk to you and you cannot see me, unfortunately.
Okay.
No issues. It's working.
So hello to everyone. Today I'm going to talk about dose optimization, but since optimization is such a big field, I'm going to focus on the verification of dose data and identification of errors. And so I'm not going to talk about how you can manipulate the parameters exactly to optimize the data, just how to verify your dose data. When we're talking about radiological protection, we have three key principles. The first one is the justification. That's actually something that we as medical physicists are not so involved with. It's more the responsibility of the radiologists or other medical doctors. It means that every radiation exposure should do more good than harm. So before we actually do an examination, the radiologist should decide whether the benefits of this exposure or this examination, so the diagnostic information we get from it, is better than the side effects, the negative effects of the radiation. And that's actually one point that in Germany would do a lot of good if people would just stick to this justification principle. Then the next one is the application of dose limits. The dose limits do not respond to the medical exposure of patients, but we're talking about dose limits for medical staff or the general population. And then the third one, that's the big one, that's the optimization. It says the number of people exposed and the magnitude of their individual doses should be kept as low as reasonable achievable. That's the famous ALARA principle. And we're talking here about the exposure to patients, the exposure to the staff, just everything. But what is also very important is the word reasonable here. So that's where the medical physicists come in, where they have to start thinking, where they have to switch on their brains and decide what is reasonably and what can we actually achieve with really reason and not just what is possible. So I would like to give you an example. Just imagine a radiologist doing an interventional procedure. Then, of course, this radiologist wears a lead apron or something to protect themselves from the radiation. And the thicker you have, the thicker you make this material of the lead apron, the better is the protection, of course. But on the other side, if it's thicker, it's also getting heavier. And so that's where the reasonable part comes in. At some point, it is not reasonable to make this lead apron thicker because you don't have a big effect from it, but you have the negative side because it's getting heavier. And that's also when you think about the optimization of dose for the patients, you can achieve quite a lot, but at some point it's not reasonable anymore. So if you're now motivated to do some optimization in your department, then you probably start where do I start with the optimization process? Because you have different X-ray machines, you have the traditional X-ray machines, you have computer tomography systems, you have fluoroscopy systems, and with all these machines, you do lots of different types of examinations. So you have to figure out where do you start with your optimization process. And a good way to do this is with these 3 steps. So you start with the first one and say, you look at those reference levels or diagnostic reference levels that we saw earlier and figure out if you have any examinations that exceed those diagnostic reference levels. Especially if you have legal those reference levels, then it's always a good idea to stick or to try to apply those dose reference levels first. Then in a second step, if those diagnostic reference levels are all okay for your institution, you look at all the examinations that are performed quite often or are involved with a high exposure. For example, if you do an examination just once a year, then you only help 1 patient by optimizing this protocol. So that's not reasonable. You only have a limited amount of time and resources, so you should invest them carefully. And that's the same with examinations with high exposure. If you have examinations that are not involved with high exposure, then it's not reasonable to start with those examinations, but you should, on contrast, do the high exposure examinations first. And then in the third step, you can go on in regular checks, go to your routine protocols, and also go back to step 1. Maybe the diagnostic reference levels have changed. We saw that they should be updated regularly. And so you would go on to a routine check and optimize all the protocols, all the examinations in your institution. One point I'd like to point out is that dose optimization does not automatically mean dose reduction. In most cases, yes, it does. But in some cases, it could also mean that you have to increase the dose to get a better image quality. And in those cases, dose optimization means dose increase. So Now I'd like to give you some examples from the computer tomography from those 3 steps. The first one is to check for those reference levels. Here you can see the CTDI values for some of our CT neck scans over a certain amount of time. You can see here the solid red line is our dose reference level. And here the dashed green line, that's the mean value for all those CT neck scans. So generally we could say we are only at 2/3 of the DRL. So actually we're doing very good. But you can also see we have some values that are very high and they're exceeding the DRLs quite a lot. So if you're looking at this, that's basically twice or more than 2 times the DRL. So you should have a look on why you're exceeding those values. The first thing you could ask yourself, is it because those are obese patients? Because those reference levels or diagnostic reference levels are not limiting values. You are allowed to exceed them if you have a valid reason. And obesity is one of those reasons. So let's have a look if those patients might be obese. Here you have the scanogram or radiogram CT scan from one of those scans. And maybe you can already see from the image that it's not an obese patient. When we're looking at the exact values of the patient, it was 180 centimeters, 79 kilograms. That's a body mass index of 24. And that means for a European, that's perfectly normal. So it's not an obese patient, and we can rule that out. Then you can see here that the patient had had some dental work done. So your second thought might be, is it because of metal implants that the automatic exposure control of a CT scanner was somehow influenced and increased the dose for those patients? And you can have a look at that by checking the modulation of the tube current. You can see here where the dental work was done. There's just some ripples in the tube current, but not really a high increase. So again, we can rule that out as the reason for the high doses. But what we could see from the tube current modulation, that it was somehow odd. Because normally a typical modulation for a neck CT scan should look like here on the left. You superimpose it here with a radiogram. It should have the highest dose in the shoulder area because there the patient is very wide. There are a lot of bones inside the body. So there should be the highest dose. And when it comes then to the neck area, it should decrease. And here again at the head part also quite low. But for all those scans, we had the high doses. We could see that it was exactly the other way around. We started with the lowest dose and then it was increasing to very high values. And that should not be normal for a neck CT scan. We were looking for the reason why for some patients the dose modulation wasn't working, and we found it in the DICOM header, or we found there a clue here at the body part examined. It said chest and not neck. So this was because this neck protocol was based on an old chest protocol, and someone forgot to change the body part and it stayed with chest. This doesn't seem like a big mistake, but whenever you have a chest here, our CT scanner requires a topogram or radiogram scan in the anterior posterior direction. And for a neck scan, we have a lateral one. So most of the time, this isn't actually a big problem. When we're just doing a scan of the neck, like here on the left side, then we have the lateral radiogram, and that is used for the tube current modulation. So everything is fine, and that's why most of our CTDI values were perfectly in the normal range. But every time we were doing not only a neck scan, but also, for example, one of the chest or some other body part, then we suddenly had two topograms. one for the neck in the lateral view, and one anterior posterior one for the chest. And then the CT scanner, because for the body part chest, it required an AP topogram, used the wrong topogram as basis for the tube current modulation. And because the topogram ends here, the CT scanner didn't know what to do when it comes up here in the head part, and so it increased the dose. So we simply changed the body part to neck, and then our dose values were perfectly fine again. Then the second step would be getting an overview of all the examinations you do at your institution. So here you have all the different protocols we're doing at one of our CTs over a certain amount of time. You don't have to worry if you can't actually read the protocol names. I made the font size small because they are not really important. What I just wanted to stress with this image here is that you have certain examinations that you do very regularly, probably daily, and then you have others on the other side that you do very rarely. Especially at our institution, because we are a university hospital, we have certain protocols we just use for studies, and so they're not used very often. And then it means that obviously you would focus all your energy and all your resources on examinations here on this side of the graph first to optimize them. But what you can also see from this overview of all your studies and protocols you use is maybe that you have some protocols that are not in use anymore, or as I would like to show you in this example, that maybe you have actually doubles, because we here had a protocol for the abdomen in a low dose version that was just called abdomen low dose, and then we had a different one that was called abdomen low dose new. So this abdomen low dose protocol is a protocol that you would use to figure out if a patient has kidney stone or something alike. You don't need high doses because kidney stones just have a high contrast and just stand out in the images. So you can work with a very low image quality. And that's why you can use low dose protocols. What you probably can see is this protocol has a much lower dose than the new protocol compared to our dose reference level, because we don't have one for the low dose protocol in Germany, just for the regular one. They're both lower than the reference level for a standard abdomen, but you can still see that here there's a huge difference. And this becomes more prominent when you actually look at our standard protocol for a regular abdomen, because then you see that there is pretty much no difference anymore. And you wouldn't really call this protocol here a low dose version, because it's pretty much the same dose as a standard version. So I discussed this with our radiographer who's responsible for CT, and she told me that this one here was actually just a protocol for testing and shouldn't be used in routine scans. So we both agreed that we just delete it from our CT scanners, and now we are just working with this one again. And so if you compare the dose from the low dose version here to the standard protocol, it's pretty much half of it. So it's really a low dose version. And then the third step would be to do regular checks. For example, by comparing different CT scanners, if you have more than one or other equipment. Here you have an example of our chest CT scan from all three of our scanners. And again, here you have the reference value. It's 10 milligrays for the CTD eyeball, and you can actually see that all of our scanners are below it. But you probably also see right away that scanner 2 has a much higher dose than the two other scanners. And this is even more surprising because scanner 2 is actually our most modern scanner. And so you would suspect that the dose there should be the lowest of all scanners. when you see something like that, you would optimize the dose from that scanner, obviously, and that's what we were doing. And we were able to reduce the dose to less than half the original one. So in the end, I would like to show you some other examples from other modalities and also show you what optimization also means. So here I have some fluoroscopy system. You have the dose values, the DAP for transarterial chemoembolization, or TACE in short. It's a procedure that is done to patients with liver cancer to block the blood supply to the liver tumor and to bring the chemoembolization particles right through the tumor. So it's also a regional chemo therapy. We have a dose reference level here at 23,000, but that's not so important. You can see that most of our values are way below it. Few ones where the doses are higher, but I don't want to focus on those right now. Let's just have a look at the ones down here at the bottom a bit closer. And when we spread it out a bit more, then you can see that one of our systems here, system 1, has a dose that is about 3 times the one from system 2. So in this case, you would probably say, okay, we should optimize system 1. But with this example, I want to point out it's not always possible to optimize, because system 1 is just an old system, while system 2 is very modern, has a lot of techniques that can be used to save exposure and radiation exposure. So in this case, it was not possible to optimize system 1 to get it to the same level as system 2. And that can also happen to you. So I'll keep that in mind, that it's not always possible to optimize systems. The only way you can work with those systems now is to say that maybe if you have risk groups like pediatric patients, you shouldn't use system 1 for those, but rather system 2. Then here you have the values for different radiologists for cerebral angiography. These box plots show that there are certainly deviations between those radiologists. I think that's very straightforward. But if you have a closer look at who is doing the examinations, then you can see here that the blue ones are the fellows, so the younger doctors with not that much experience, while you have here the senior physicians who have more experience. So you can see that the box plots here are much smaller. The mean values are usually lower, and that's just because of their long experience. And that's another type of optimization here. What you could do, obviously you wouldn't optimize the systems because they're all using the same systems. But in this case, you would rather say, okay, maybe you could instruct the fellows how to use the systems properly. Maybe they don't know about certain functions that you could use to reduce exposure. And that's also another type of optimization. And then here, my last example, I also want to give you an example for radiography. That's the chest radiography with all our stationary systems in the posterior anterior view. Again, here you have the dose reference level in red. It's 15 micrograys per square meter. And you can see that most of our chest radiographs, again, are below the value. So you could say most of it is okay. But again, here are some outliers, and you should have a closer look at why there are outliers. So what we were doing is spread it out according to when these examinations were performed. And maybe it becomes more apparent when I do it like this, because you can see that here are usually our normal working hours during the day, and everything that's marked in blue are working hours outside the normal day-to-day routine. It's when we only have a reduced number of staff. And while here during the day, we use a dedicated system for our chest radiographs. outside of those regular hours, we're using a different system. And so we can say whenever we're using the different system, the other system, we have those high values. And so we could immediately see, okay, that system is responsible for the high values. And actually it was because this system wasn't able to deal with the high KV values that we use for chest radiographs. So the answer to that for the optimization process would be to use a different system that is able to use the high KV values for chest radiographs. So to sum everything up, dose optimization is very important. I think you all understand that. It's not to discuss, but you only have limited time and resources, so you should invest them very carefully. Focus on examinations and protocols first that are really worth optimizing. And I hope you saw that there are various means of optimization. So of course you can reduce the parameters or manipulate the parameters from your scanners, from your systems, but there are also other ways. So for example, teaching or just finding out which machines are the best to use. And with that, I'd like to thank you for your attention.
Thank you, Engineer Catherine Inch, for your nice lectures. I hope everybody has understand your importance of dose optimization in diagnostic radiology. So we are going for the next speaker. I'm just showing his biography. Professor Dr. Ghulam Abu Zakaria. He is the next speaker and he will talk on the radiation protection and quality management in diagnostic radiology. He is the former chairman and chief medical physicist at the Department of Medical Radiation Physics, Gummersbach Hospital, Academic Teaching, University of Cologne, Germany. And just a minute, okay. Also, he is the professor of clinical engineering at the Faculty of Electrical, Mechanical and Industrial Engineering, Anhalt University of Applied Sciences, Cologne, Germany. He has experience in teaching and clinical work in medical physics and clinical engineering, more than 40 years in Germany and 30 years in Bangladesh and other developing countries. He is the board of directors of Global Oncology University under Harvard Medical School, Boston, USA, since 2019, awardee of the Global Radiation Oncology Distinguished Leader Award 2019 by the Global Health Catalyst of the Harvard Medical School. In 2018, he is nominated as the chairman of Accreditation Committee 2, the IMPCB, and he is also a vice chair of the IOMP Accreditation Board. He is the honorary advisor of National Institute of Cancer Research and Hospital in Dhaka, Bangladesh since 2010. He is honored with from the Oncology Club and Circ Federation of Oncologists, a highly prestigious award, Outstanding Personalities of the Decade 2000 to 2010 for the unique contribution to establish medical physics in Bangladesh. He is the honorary member of the Bangladesh Cancer Society in Dhaka since 2009. He is also acting as a professor of Anhalt University of Applied Science, Germany. Since 2001, he's the chairman of DGMP, that means German Society of Medical Physics Task Group for the developing countries. He's the founder, patron professor, and coordinator for the International Cooperation of the Department of Medical Physics and Biomedical Engineering in the Government Vishwavidyalaya, Savar, Dhaka, Bangladesh. From 1987 and till 2019, he's the former chairman and professor of the Department of Medical Physics in Gummersbach, University of Cologne, Germany. So I will request Professor Ghulam Abu Zakaria to present your lecture. Thank you.
Good morning, everyone. Thank you very much, Madam, introducing me to this audience. I will just, I'm very happy that three speakers has given many informations and also important lectures on diagnostic radiology and radiation protection. I just here summarize some data and practical hints, which is may be important for medical physicists working in the diagnostic radiology. Can you hear me good?
Yes, yes.
Yeah, okay. So my topic is radiation protection and quality control in diagnostic radiology. So I will show you first some photos, maybe interesting for you. Most of you know this. The radiation in medicine started with three discoveries, you know. I can say this is the discovery which allowed to have a profession medical physics, because earlier time we use also many invention in medicine, but at that time there is no profession of medical physics. Through these three invention, we come not only the subject radiology and radiotherapy, but also the subject medical physics. It is the invention of X-ray by Professor Röntgen in Germany in 1895, and after 114 days later, there is another invention. This is natural radioactive by Henry Becquerel. It is 1896, and after that, the invention of radium-226 by Perret and Curie in 1898. You see here some stamps given from different countries, especially here Monaco. Here is a historical. You have, everybody knows the Konrad Röntgen, and radiologists they observe the days of Röntgen, but you see here he has worked with the cold cathode, and this cold cathode is actually a tube with rarefied gas and two electrodes, and when you apply voltage, and the rarefied gas is ionized, and this rarefied gas hit the anode and it produces the X-ray. Yeah, it is just, we say, cold cathode. That means inside the rarefied gas and simply two electrodes. And the modern one is invented by Coleridge, and he has the idea to make the tube vacuum and also introduce the filament, heating filament, so that you can adjust the different voltage and current, and you can control what you like. This is actually the hot cathode, and hot cathode is used still today. And we show you another picture. It is, you see the Madame Curie. We are also in medical physics, International Medical Physics Day after her name. She's actually discoverer of natural radioactivity with his teacher, Henry Becquerel. And here see her daughter, Irene, here. She's actually is the inventor of artificial radioactive. I put a very nice here photo. I like this photo because everybody knows Madame Curie is an inventor of radioactivity, but she is also very social responsibility. She works in the First World War with her daughter Irene, and they went to the wounded soldier of First World War, and they do the X-ray examination and help millions of people. And here is actually one photos I have given at the beginning of X-ray and radioactivities. At that time, the question is that there is no radiation protection. So the people are doing exposure like the photo in left and right, and you see many damage here, the hands you can see. So I start my lectures with the radiation protection. You see, it is actually a definition I have taken from the book, scientific and technical field which serves to protect people, property, and environment from harmful effect of radioactive substances and ionizing radiation. And for this purpose, we have some documents, laws, regulations, and guidelines. The most important international, this ICRP report 103. This is actually the current one in November 2007. And based on this original international protocol, the European Council has given this protocol. That is, I'm just talking from Europe and Germany, and it is also similar to other parts of the world. And based on the European documents, the German, in Germany, we have a German radiation protection law. It is given in 2017. And of course, an ordinance is given 2019. And these both are now currently applied in Germany. And I'm going to tell some data in the next slides. And in Germany, of course, this DIN norm is very important parts of all the regulations and procedures of radiology. Here, many documents, most of them, this radiation safety series, and it is from IAEA. But in Europe and in Germany, you see many documents. And these documents are used, for example, here, when you want to do expert in radiology, you should know how many times you need it and what is the curricula you should absorb. And here is the radiation protection laws, and it is the ordinance. Here, I give you this one is the old ICRP report, and this is the new one. I just told you already, ICRP application 103. Here, once again, I just summarize this. This is an ICRP, and you see it is the European Union, how they are transferred to their countries, and here is the Germany. Yeah, for example, ICRP 103 2007. It is actually applied in 2013 in European country, and Germany it's come to 2019. That means there is difference 2007, 2019, 12 years. So when there is an international recommendation, and after 10 years, it is transferred in Germany. This is everybody knows from medical physics. This is the energy dose. Yeah, it is defined, the absorbed dose per mass, the joule per kilogram, and it is the unit is gray. Everyone know this parameter, physically parameter, is very important. It can be measured, and what is important is this quantity that is directly proportional to the biological effect. So we have a very nice tools in our hand where we can measure everything very precisely, and this is the precondition of a very good treatment planning or measuring dose. And this is the equivalent dose, this is nothing. This is the measured dose in gray, and you just multiply it with the radiation weighting factors. And this is actually here. You see different radiation had different weighting factors. When the radiation type with high weighting factors have higher biological effectiveness than those of low weighting factors. And what is here important, the effective dose, it is a very important invention. This is again, effective dose is an equivalent dose multiplied the tissue weighting factor. We have already considered the radiation quality, and now we consider the different tissue factors. And when you multiply everything, then you have the effective dose. And I give you a little bit here. How can, this is the old, you can see here the here you have see the organs, different organs, and the value from ICRP 60, and this is the value for 103, and you see some value it changes because in the creation of ICRP there is some changes, and even in this ICRP 103 we have more organ has to be considered. We have considered this. And a medical physicist can calculate how they calculate. Here, maybe you have exposure a patient or a person and who is exposed with 100 millisievert in thyroid and lung and breast. And you see here the weighting factor from the old one and the weighting factor for the new protocol. And when you calculate, you can see the effective doses for ICRP is it was 22 millisievert, but now is the same exposure. You see the value is 28 millisievert. What that means, the exposure of the three organ with 100 millisievert corresponds to a homogeneous exposure of the whole body with 22 or 28 millisievert. And what is important in the effective doses when in a person, radiation worker, when he or she received less than the air dose 20 millisievert, then you can put the effective doses equal to the organ doses, what you measured your film batch. Here I have given some innovation, including the new German audience. You see here different, they have considered the new data, more details regulation on teleradiology, introduction of medical physics expert in X-ray diagnostic. This is also an important, the X-ray diagnostic you need officially the medical physicist, and recording and introduction information reporting system, and new formulation of quality assurance. And you see here detection of book and necessary risk analysis is one of the tasks of medical physics. These are all included in new audience. And here I have given you also the medical physics involvement. You see here different involvement to be consolidated for close cooperation. You see here consolidated. But what is important for us in radio diagnostic, that the CT and in interventional radiology, we need medical physics, medical physics. You should have, according to the number of machines and tags, you should have a medical physicist. And here I have given the different works, what medical physics is doing in radio diagnostics. Yeah, here you see the quality control, choice of instrument, monitoring, and what Dr. Joya told, the monitoring of diagnostic reference level, investigation of incidents, and carry out of risk analysis. These are the things which is the main domain of medical physics in radiation in radiology. Even in Germany, we have not too much medical physicists in radio diagnostic. In the coming years, we need more radio diagnostic medical physicists, because in Germany most of them are physicists in radiotherapy, and they are not fit for the radio diagnostic. So it is a huge task to produce radio diagnostic medical physicists. Here is the current fluoroscopic interventional cases. I do not go to read everyone. You see here many clinical application. You have the interventional radiology and CT, and here we need medical physicists. Yeah, I can read one. You see here the percutaneous treatment of duct system of the gastrointestinal tract. Here you need the, that means the places where the higher doses is applied, and there you need the radio diagnostic physicist. Here is also a good information for reporting system when there is an incident. It is actually write very well when group and person. You see the measure types and threshold types and values and frequency. When you have this table, then as a medical physicist, you know when is the action threshold and when is reporting threshold. And according to this, you should do your work. For example, the diagnostic fluoroscopy reporting threshold. Yeah, this is DFP when greater than 20,000 centigrade. On once frequency, you should have the reporting threshold. And you should have the measure to prevent such incidents. Yeah, this is actually important what we are doing. Execution of technical quality assurance. This quality assurance in the most important things. Instruction of the radiation workers in Germany or in Europe. You have an instruction at least once in a year. And the training of equipment, that means when there is a new equipment, even when is old equipment, you should give the training of the radiation workers. And the continuous qualification of the staff, this is also important. You send them to different training course. And this is also identify checks the patient and monitoring the PIM, and regular meeting of a working group and prevention of incidents. As regular, you should meet and then you can prevent the incidents. So I go quick. Here is actually the, you see the different things what you needed for the installation of a machine. Yeah, you see here manufacturer documents, acceptance testing, expert examination, equipment instruction. These are all things needed for medical physics to install a machine in a department. Here is a dosimeter. What you needed was, this is a survey meter, and you see these are all batches what's needed. And here is the area. Everybody knows this, that the 20 millisievert per year is actually the effective dose for a radiation worker. And there is a control area and monitoring area. There is a two types of category. You can divide it, the personnel, two category, category A and category B. When the category A, they have the maximum possible, the 20 millisievert in year, but in category B, then you have up to 6 millisievert per year. But there is a difference between category A and category B. The category A, you need once in a year medical examination, but in category B, you do not need this. That's why you have more other things to do. Here is the rules. I give some important data from the European and German. You see the category A and B I told earlier, and 20 millisievert per year. And what is important for women, in women, childbearing potential, the dose per month to the womb not exist 2 millisievert. This is actually important. They also in year 20, but do not exceed 2 millisievert per month. And what is the, for an unborn child, then the woman in the 9 months is only 1 millisievert. And there's an occupational light dose, 400 millisievert. And you see here the effective dose, it takes account an effective dose equal to the organ dose when it's less than 20 millisievert per year. And here is actually these three requirements is every radiation worker need this medical examination A category once in time, bearing the official personal dosimeter and participation in annual protection instruction I told you earlier. And here you see some archiving. I give what is actually important for medical physicists in radiation diagnostic or therapy. You just read your radiation protection law or ordinance, and you find some very, very important data, and you can this data you should teach in the all other staff in your department. For example, here all the data is giving how the archiving is. Yeah. For example, here I can say the personal dose rate in the control and monitoring is 30 years. You should actually preserve it 30 years. Quality assurance X-ray diagnostic equipment for investigation or treatment of people, accepting testing, you should 10 years, and constancy takes in 2 years. These are all data taken from the audience, and you summarize it. And this is already Dr. Jaya give you very details the reference level, and I am giving here some reference level federal office, and you see different organs have different values, and a medical doctor should maintain these values. When this value exceeded, he can exceed the value, but he should or she should explain why this value exceeded in the in your examination. And here is actually the CTD and DL for CT. Now I'm going very quick, the quality assurance. I think not as quality assurance, quality control. You can understand between quality assurance and quality control. And it is a big topic, and you know everybody as medical physicist, I want to go here the quality control. You see the goals of quality control: reduce exposure, better or consistent image quality, early detection of errors, and cost reduction. These are actually the goals of quality control. And here quality responsibility of medical physicists. What is the responsibility in quality control? Accepting testing and partial accepting testing by the manufacturer. He should just monitoring it. Examination by independent expert when there is a new machine. Constantly checks in X-ray equipment, daily, monthly, possibly 3 monthly, yearly by the user. And constancy test of therapeutic X-ray equipment, daily and half yearly. You see here, therapy machine is not available in Germany, but some hospitals still X-ray therapy machine. They should, the technician do the quality test in daily, and medical phases measure the dose in half yearly. But in the diagnostic, you see the daily, monthly, and possibly 3 monthly. When you have very good, then the authority allow you not monthly, you can do it 3 monthly. And then here, regular inspection of the image reproduction devices, monitoring quality assurance by the medical doctor chamber every 2 years. Yes, in Germany is very important because you have done everything in the hospital, but in the medical doctor chamber, they monitor your value. So you send all the documents. They say, we need the documents for all the 3 months, and you send them, and they actually examine the documents. And when there is a problem, they actually recommends is to modify this and that, and you should do that. When you are not in a position to do to change your works according to the medical doctor's chamber, then they will close your department, even in the machine. Monitoring of mammography screening by the reference center. This is special in Germany. The mammography, Catherine already told, she is actually one of the physicists working with the mammography in Munster, and they knows how they monitor everything for the mammography. Storage of obligation of data and other recordings. So I give you once again, these are the areas where quality control is done. Testing will be done. Testing and calibration of measuring instrument and test equipment. The equipment should self quality control, and image display and image processing equipment, direct radiology, fluoroscopy, mammography, CT tomography, and teleradiology. These are various. I go one by one very quick. You see here is the testing equipments. I have just here given the equipments for our hospital at the time, but it is from the factory PTV. You have other factory also, IBA or Sun Nuclear. They have such type machine. You see here, there is a phantom with fluoroscopy and the phantom with radiology. And even here you see the dosimeter and those area product chambers here, and you see here luminance meter, and you see in which equipment, in which calibration every 5 years. You see here calibration every 2 years. These are all given details in the radiation ordinance, and you should also find the radiation ordinance in your country and do accordingly. When there is no national protocol like this or a national regulation, you can take the international, or it's better to take the recommendation of IAEA. So here you see constancy of monitor, the observation monitor, test intervals I have given here, and checkpoints. So all are checking. Every day morning, a medical doctor expose this photo to the monitor, and he or she should examine all the parameters, and all the parameters is very fine, and they are in the given range, then they can start to examine in the hospital. Here is the direct radiology testing quality control. Parameters is testing optical density, contrast, resolution, radiation field dose, and dose indicator. Yeah, you just expose with a certain condition, and after that you have your value, and this value should be fit in the tolerance value, which is already fixed by the vendors. And here is a constancy in the radio fluoroscopy. You see here in the C arm, and these are the values should be checked, and quality control, this value should be in the tolerance level. Here you see the resolution, here you see the low contrast, and here you see the contrast, and even the field here, radiation field and artifacts, everything is here. And his mammography is also a very sensitive things, and in German there is some protocol. According to the protocols, you should do the quality control in mammography. You see here in mammography is more details, and all the parameters should be checked. Here is all the phantom for the mammography, and it is a little bit complex, but a medical physicist or technician learn very quickly how they manage to do the quality control in radiation. Here is an important CD-MAM contrast details, and this is done in Germany because of screening. When you have a screening, you want to screening the healthy woman, then you need more dedicated machine, as well as more important quality control. Here see the mammo contrast here. There's a many gold lips in center, and gold plates, and 16 different diameter and thickness, and all are should be checked according to the protocol. Here is the city phantoms. Dr. Jaya is described very well the physical background, and you just measure it, the CTD and DLP, and also protocol. And of course, in computer tomography, one is imaging quality control, and other is dosimetry quality control. And here is procedures of telemedicine. Yeah, and telemedicine, you see, when the medical doctors in one place and the technician in the other place, they do the experiment, and medical doctors gives the parameters. Here the accepting testing of telemedicine. This is actually little bit more than, because you should also accepting testing in the computer technology, as well as here constantly text of the machine. So my last slides, I want to see a very important place in Hamburg. This is the memorial commentators, those who lost their lives in study of radiology. Yeah, at the beginning, there is no procedures of radio protection, and many people is died. Here it is this monument in the garden of St. Georg in Hamburg, inaugurated in 4th April 1936. You see here 359 men and women from 23 countries till 1960. The name is given everywhere here. These people are died because of the radiation. And you see the X-ray diagnosis is the most well-known imaging method in medicine. One advantage of the use of X-ray in diagnostic and treatment is the detection of disease and accidents without burden invasive procedures for the patient. Opposing to this advantage, the harmfulness of high energy radiation has to be considered. Therefore, special precautions have to be taken when using ionizing radiation. X-ray laws and audience protect staff, population, and patients against the danger of radiation and to minimize damages. Here I have given my last slides. You see the radiation protection ordinance contains a list of offenses according to the Atomic Energy Act. Any violation against the regulation will be punished up to a maximum of 50,000 euro. That means in Europe, also in Germany, when there is any violation of radiation protection, yeah, then you should plenty maybe up to 50,000 euro. Thank you very much for listening.
Thank you, Professor Jakaria, for your nice informations. And we are already now, time is already reached up to our AFOMP school webinar. So I'm giving the floor, I'm requesting Dr. Rajni Verma, are you here?
Yes, I'm
Yes.
there.
Okay,
I
please,
request,
please, you continue.
Yeah. Thank you so much, ma'am. And I request all to please, all the speakers to please switch on their videos so that all the participants can see the eminent speakers. I think Dr. Catherine is with us right now. We cannot
Yes, I'm
see
here, but I'm not going to turn on the video because I
Okay.
think it's going to crash my Zoom.
Yeah, no issues, no problem. So first of all, I want to thank all the eminent speakers that they did their time from their busy schedules for having such wonderful and elaborate AFOMP school for the participants. Here we have covered almost all the things which are important nowadays for diagnostic radiology. So now we have some few queries which are very relevant to our today's program. So I won't take much time and I'll start it right away. So the first question and query is from Professor Anupama. So in your opinion, what are the challenges in implementing the e-learning programs to exercise in real clinical settings? It means, what I mean is, like, it is really good and convenient to teach people who are far and do not have access to proper educational programs. But how challenging it is to employ those people to real clinical settings, in your opinion?
Okay, thank you, Dr. Verma. Actually, you know, that's the, in this time we are feeling that we have to go for online settings. Before that, we do not have any ideas. So, you know, by the time we will develop for the medical physics, because it is most practical things. So, so we have seen that the videos and many things with the instructor has been put in the online. So I have shown in my PowerPoint that the blended learning is very important, because through online we get some advantage, and also for practical things you have to go hospitals and then see, and some hospital things, not all the things. Maybe if you would like to see the equipment first things, and then you have to show the procedures, you can show in the video, and it should be done very meticulously and clearly for the instruction, but that means for the education for the professionals. So when it will update it and will show in the through online, then when you will go again into the hospital, then they will do hands-on and it will be more effective, I think so. Thank you.
I agree with the ma'am that with this e-learning programs combined with a short exercise or a planned training can be very fruitful for the developing countries, that we are always lacking in some fundamental facilities. So thank you so much, ma'am. And now I have a next question for Dr. Jayasingham. He has joined us all the way from Sri Lanka. So, sir, I just want to know, what do you feel? What is the long-term impact of establishing DRLs?
What is the?
What is the long-term impact in quality of diagnostic radiology after implementing or establishing DRL, reference DRLs?
Yeah, I think that I have discussed that. So then initially we established in each year, then after that every 3 years. So when you optimize your protocol DRL, then you can the aim of radiology, the maximum, increase the quality and with minimizing the dose. So then finally you can achieve the high quality image with minimum dose. So nowadays there are different technologies available. Now AI technology included in the CTI. So then you can produce the image with minimum dose, then you can increase the image quality using artificial intelligence like that. That's our overall aim, to reduce the dose and increase the image quality.
So what I want to ask is, how much you feel it is relevant? Like right now already, whatever machine you buy, it comes with already AI, means that automatic exposure parameters, it comes with those parameters.
Yes.
Now we are establishing DRLs for our developing countries. So how relevant it is, if we, means how much impactful it is to feed our data to those machines and use those parameters for imaging in developing countries, or for the Asian ethnic human body.
Yeah, actually that we in developing country we don't have much DRL. So now we are started to establish the DRL, but it will go a long time to achieve those things.
Okay, thank you so much, sir. It's a big program. I think we will see the outcomes in the coming years very clearly. It's a developing field now for the, or developing project for the developing countries. Thank you so much, sir. So now I have another question for Catherine. I would say a liberty to directly call her from her first name. So, Catherine, as you are a part of lots of optimization program and the auditing programs, so I want to ask you your experience about auditing programs in diagnostic radiology and their impact on the radiological procedure and the quality of a radiological procedures, what we do in hospitals. How much impactful the auditing programs are? I mean, about your experience in Germany.
Well, we have all different kinds of auditing programs here. We have internal ones just in our departments where we get together and decide what do we optimize, where can we start. And then we also have a lot of external audits from physicists, from medical experts. So especially the value from the external experts is quite fruitful, because they have a different view and they also see other departments, other clinics, and they can give us their experience. And so I think these audits are quite useful.
Yeah. Thank you so much, ma'am. Indeed, they are quite useful. We in developing country also, we are also looking forward for the regular auditing programs. So now I move on to our last question, and this is from Professor Zakaria. Professor Zakaria is a big name in the field of medical physics, not just in developing countries, but also in developed countries. And he's been part to various regularity making projects. So I want to ask him, like in developing countries, the radiation protection protocols are quite established for the radiotherapy things, but they are not as stringent as for diagnostic radiology. They are not very stringent as they are for radiotherapy. So what do you feel in the near future, what is the role of national regulatory bodies to ensure radiation protection and quality in diagnostic radiology?
Yes, this is actually, thank you very much for the questions. Yes, you are right. The quality control may exist in the radiotherapy in developing countries, but I'm not sure every developing country has a very good infrastructure of quality control radiotherapy. I know many countries, they are doing quality control not so good, because the regulatory authorities do not monitor it. Yeah, they are doing something according to the advice of the vendors, and they are spending more time with treatment planning. When they are doing treatment planning, medical doctor is satisfied, they think they are the best medical physicists. This is not the criteria. We have an international protocol. According to the protocol, the medical physicist should do all the quality control, and this should be checked by the atomic agency when they do not check. And I have seen up to 50,000 euro penalty when they do not check it. Is this infrastructure exists in developing country? No, most of the country is not existing. Even in radiotherapy is a problem. In radio diagnostic, it is actually, I think there is no infrastructure at all. Yeah, because the people in the atomic energy, yes, some countries, maybe in India or other more developed countries, they have some infrastructure like this. Sri Lanka, I think it is a very nice radio diagnostic structure. But I know other countries, there are no structure. So you see in diagnostic radiology, the radiation protection is more important than radiotherapy. Yeah, how many center radiotherapy in a country? How many people come contact with the radiotherapy? Even in Germany, maybe 150,000 people come contact in radiotherapy, but 84 million people come to radiodiagnostic. When there is a good radiation protection and quality control not in radiodiagnostic, then there is a problem with radiation protection and so. So I think the IAA should more strict, and they should give the regulation to the developing countries so that radio diagnostic quality control and all the regulation should come in future. This will start with the optimization of the reference value, just like Dr. Zaya showed it very nicely how you start. Yeah, just an survey and fix your data, and when the data is fixed, you can compare with other countries, and this is actually starting point. And I have shown, you should have the very good procedures. How can you do the quality control daily? So actually, the government and the Atomic Energy Center should come forward and do some regulations. And what is also important in developing country, they should not have the officers the knowledge of quality control, but this is not a problem. They should maintain a pool, some special medical fees in medical doctors from different hospitals. They should have a pool, and with this pool they can start the quality control.
Thank you so much, sir. Yes, indeed, I agree that national regulatory bodies needs to be more active in the developing countries if they have to ensure the radiation protection and the quality in diagnostic radiology. So I must thank all the speakers for today's wonderful talks and informative, elaborated presentations. And I also want to inform all the participants that this is the whole all the speakers today are the quite active team in whole Asian and developing countries. They do a lot of work for the developing countries and the students out there. They are, I'm not sure, they are mentors to, I think, some hundreds of students. And especially Professor Anupama used to do lots of awareness programs for even for the poor and needy people in her country. So we must always support that. And I must thank ma'am that she is doing a wonderful job for the students and for the people. And of course, Professor Zakaria's cooperation is always there for the people from us, especially from developing countries. And they are indeed providing us quite a role model from their work in Germany. So I thank them all once again. And I also thank all the participants for their active participation in joining us. I hope you have enjoyed the scientific feast to its best. And we are looking forward to see you for our next monthly webinar. So I must say, I take your leave and thank you all for joining us. So
thank you, Rosni.
Thank you, ma'am.
Thank you, Dr. Verma, for the nice moderation. And
thank you.
Thank you all. Thank you. Bye-bye.
Thank you all. See you again.
See you.
Thank you, Dr. Jaya. Thank you, Catherine. See you all.